All right, ladies and gentlemen, so we are starting the Unit 1 problem set. This is the problems, the actual calculations you had to do for 12 through 16. All right, so number 1 says a high school athlete runs 100 meters in 12.2 seconds. What is the velocity in meters per second? All right, so we're asked for the velocity. So our equation is going to be V equals the change in position over time. So this 100 meters represents the change in position. So delta X is 100 meters. Time is 12.2 seconds. We're looking for velocity. So we're going to have V equals 100 divided by 12.2, and so that should equal 8.2 meters per second. Just a general chug and plug, doesn't get any simpler than that. All right, number 13. A horse canters away from its trainer in a straight line, moving 150 meters in 14 seconds. It then turns around abruptly and gallops halfway back in a straight line in 4.5 seconds. So it says to draw like a line diagram. Oops, that's not straight. But I'd recommend actually doing a position over time, and I wouldn't worry about scaling it or anything. This is just kind of for as like a reference for you. So it's going to start at the origin, and it's going to go 150 meters. So I'm going to make this right here 150 meters, and then this time right here is going to be the 14 seconds. I'm going to move my T, it's in the way. Here we go. And then it's going to gallop halfway back. So this is going to be halfway back, and that time is 4.5 seconds. So 14 plus 4.5, this gives me right here 18.5 seconds. And I know that this position is halfway between 150 and 0. So that's going to be 75. And that's in meters. Okay, so for B, we want to calculate the average speed. Okay, so the average speed is total distance over total time. So we're going to use the equation S equals D over T. D is equal to 150, the first leg, plus 75, the second leg, which gives us 225 meters. The time we already added up, but just for clarification, the first segment was 14 seconds. The second segment was 4.5. So 14 plus 4.5, that is equal to 18.5 seconds. And now we just plug those in. So S equals 225. It's not 220. There we go. S equals 225 divided by 18.5. So S is equal to 12.2 meters per second. All right. And now for velocity. Okay, so velocity is equal to the change in position over time. So when the horse started, it initially started when VI was equal to 0. I'm going to erase this P because it's in my way. And then its final position is at 75. So VF is equal to 75. And then the time that it took the horse to go from VI to VF is still 18.5. So change in position is going to be your final 75 minus your initial, which is 0. So you're going to get 75. And then the time is equal to how long it took the horse to get 75 meters. So that's going to be 18.5 seconds. So V equals 75 over 18.5, and that is equal to 4.05 meters per second. So there's 13. Yay! Okay, 14. Here we go. So on 14, on an ill-started Monday morning, Doc Schanfeld started the 235-meter walk to her classroom. About 75 seconds and 120 meters into her walk, she realized she left her Sarah donuts in her car. She stopped, turned around, and walked 65 meters in 20 seconds, only to realize she did have the donuts. She stopped again and contemplated whether to go to work or call it a day. I mean, can you blame her? If I realized I had done all that, I don't know. Probably not the best start to my day. So again, I'm just going to do a quick position and time graph. So the first part, just ignore this first sentence because that 235 meters really has nothing to do with the problem. Okay, so about 75 seconds and 120 meters into her walk. So she went 120 meters. So I'm going to call that right here. So that's going to be 120 meters. And then that time was 75 seconds. Okay, she stopped, turned around, and walked 65 meters in 20 seconds. So we have to do 120 minus 65. Okay, so this distance right here is going to be 120 minus 65, which puts her at, that goes there, 55 meters. Okay, that's 55 meters on the graph. Okay, so that, and that took how long? 20 seconds. So we have to do, for our time, we have to do 20 plus 75, so the whole time at 95 seconds, she's at 55 meters. Okay, so let's calculate the average speed. Speed is equal to the total distance over the total time. So speed is equal to, oops, forgot. So we have to do the distance that she walked. She walked 120 meters in 65 seconds. So 120 minus 65. 120 minus 65. We already really knew that. It's 55 meters. And then the time is going to be the 75 seconds for the first leg. And then the 20 seconds for the second leg. So 75 plus 20 is 95 seconds. So we're going to do S equals 55 over 95. So S is equal, oh, ding dong, look what I did. I subtracted here instead of added. I knew something that wasn't right. So 120 plus 65, oh dear, okay, is 185. Yes, that's better. So this distance is 185. I was doing velocity. Ding dong. All right, so S is going to be 1.95 meters per second. All right, now we can do velocity. Velocity is equal to the change in position over time. So our change in position is going to be our starting position, which is at the origin, which is going to be 0. And the 55 meters, I don't know why I'm putting a V. It should be an X. This should be an X, duh. Okay, so XI is 0, XF is 55. So we're going to do VF, 55, minus 0 is 55. Shocking. And then the time is still the total time, which is 95 seconds. So V is equal to 55 divided by 95, which is equal to 0.58 meters per second. Okay, so that's good. And then we have one more of these to do before we do something else. All right, Tony, he's my son. He has lost his Ninjago, one of his Ninjago Legos. Story of my life. This time is Air Jitsu Cole. On his way to plead for help in finding his toy, Tony runs 70 meters in 36 seconds before turning around abruptly and walking 47 meters in 50 seconds before giving up in utter devastation over his lost Air Jitsu Cole. And you better believe he begged for a new one. All right, so here we go. Position and time. So on the first leg, he goes 70 meters in 36 seconds. So I'm going to put this right here as 36 meters, and then the time right here is 36 seconds. And then he turns around and walks away for a total distance of 47. So I need to do 36 minus 47. So he is going to walk 47 meters, which is going to put him at the position of 11 meters. Wow, that's a really big distance. Okay, at any rate. And so it takes him 50 seconds to get there. So 36 plus 50 is 86 seconds. So when he is done with his little whatever, it's been 86 seconds. 36 seconds to go 70 meters, and then 50 seconds to go 47 meters. Wow, we need to get him on like the Olympic committee or something. Okay, so let's calculate the average speed. So S is equal to D over T, the total distance over the total time. So his total distance is 70 plus 47, which is going to give us 117 meters. Our total time is going to be the 36 seconds plus the 50 seconds, which is going to give us 86 seconds. So we're going to plug that in. Of course, we're looking for S. I usually forget that part. All right, so S is equal to 117 over 86. So S, it's not going too fast, is equal to 1.36 meters per second. All right, and now for the velocity. Velocity is equal to the change in position over time. Change in position is going to be your starting position, VI, minus your final position, which we've already found. I keep doing that. Why do I keep putting a V? I think I see the V in the equation, and that's why I'm doing it. So XI is 0. XF is 11. So change in position is going to be 11 minus 0. Final, I did it again. Position minus starting position. So we're going to get that to be 11 meters. All right, and then the time is still took 86 seconds to get to the 11 meter mark. So that's going to be 86 seconds. And we're looking for velocity. So velocity is equal to 11 meters divided by 86 seconds, which gives us an average velocity of 0.27 meters per second. And there we go. Okay, so now onto the position versus time graph. So position is on the Y, time is on the X, and the first thing we need to do is to graph these spots, graph this data. All right, so we're going to do 2, 4, 6, 8, 10, and those are in seconds. And for the position, we're going to do 5, 10, 15, 20, 25, 30, and those are in meters. So let's see. Time 0, first data point is 0 over 10. 0 and 10, that's done. 1 and like 12 is B right there, that's done. 2 and 14, that's done. Now we skip over to 5, and we go up to 20, so that's done. Over to 8, up to 26, there's that point. And then 10 seconds and 30 seconds goes right there. Okay, so I graphed all my points, and they make like a nice straight line. Okay, so there's A, there's the position time graph. All right, and then let's see, we have to figure out how far from the starting point is the skater at 6 seconds. So at 6 seconds, she's right here, or he. Robin, I guess, is kind of a unisex name. So, I don't know, 22. So he's at position 22, but they want to know how far is the skater from the starting point, which was 10. So to find the position, the change in position, we have to do the final position minus the starting position. So 22 minus 10 is 12 meters from the starting point. And how do you know? Well, because you know that it started at 10 meters and ended at 23 meters. All right, now for number 3, we need to write a mathematical model to describe the curve. So I'm going to do that in green. So that means we have to do y equals mx plus b. So first thing we're going to do is find m. M is equal to the change in y divided by the change in x. All right, so the points I'm going to pick this point right here, which is at 10 and 30. And then I'm going to pick the starting point of 0 and 10. So let's see here. We're going to get 30 minus 10 divided by, 10 minus 0. So my m is going to equal 20 over 10, which is going to get me 2. All right, so B is where the graph, the line crosses the y-axis. So B is going to be at 10. So my equation is going to be y equals 2x plus b. No, plus 10. Come on, pay attention. Okay, and then the last thing we need to do is figure out, was this be constant over the entire interval? How do we know? Yes, it was constant. Yes, it's constant. And we know because all the points are on the line, or something to that effect. Alrighty, so there we go. That's your problem set, numbers 12 through 16.